Welcome our first speaker. He will talk on polarization patterns of ferroelectric nematics. Let's welcome Oleg.
Thank you, Ivan. Thank you, Ergir, for inviting me here. I would like to present the work that was done primarily through the experiments at Kent State University by 3 graduate students shown here. It's Priyanka Kumari, Vijaya Basnet, and Kamal Thapa, with the help of postdoctoral fellow Satyanarayana Paladugu, and in collaboration with our colleagues in Kyiv, Vasil Nazarenko and Natalia Aryasova. We also enjoy some help in modeling from 2 theoretical physicists, Sergei Shayanovsky and Maxim Lavrentovich, and also from 2 mathematicians whom you probably know, Dmitry Golovatiy and Peter Sternberg. So the material we are exploring is very new. Despite the fact that it was predicted in 1916 by Max Born, this material has been discovered only very recently, between 2017 and 2020. It represents a ferroelectric nematic liquid crystal. So it's a fluid formed by elongated molecules with huge dipole moments. There is no positional order, and the molecules point in the same direction. The picture that I show here kind of represents a mental impression of how this ferroelectric nematic would look like. But in fact, if you think a little bit more about this picture, you would realize that there is a problem. Any sample would have boundaries, and if the boundaries are perpendicular to the polarization vector, that deposit electric charges. And these electric charges would create the so-called depolarization field shown here. And if you estimate this depolarization field, it's many, many orders of magnitude larger than the electric fields typically used in experimenting with nematic liquid crystals. It can even destroy the polarization order. So the problem of depolarization field is not new. It has been addressed in the past for the solid ferroelectric materials by Landau and Lifshitz, and then later on by Kittel. And the suggestion was that in order to reduce the depolarization field, the system splits into domains. The domains show anti-parallel arrangement of the polarization. That way, the surface charges alternate between positive and negative, and the total field decreases. So the scheme obviously accounts for the underlying symmetry of the material. In the solid ferroelectric, it's the crystallographic lattice, and the polarization is more or less tightly related to the crystallographic axis. Here you see that the domain walls form straight lines or straight walls, and they separate domains that are rectilinear with opposite directions of polarization. So our question was, okay, the ferroelectric nematic is a fluid. There is no crystallographic axis. So how this depolarization field problem will be solved in the nematic fluid? And we decided to start with very simple experimental settings. In one case, we would deposit the thin film of a ferroelectric nematic on the isotropic fluid substrate. It's a glycerine. There is no in-plane axis in such a setting, and the ferroelectric nematic can adopt whatever structure it wants. Then we will make the problem a little bit more difficult by placing the film of the ferroelectric nematic between 2 plates, and one plate is still azimuthally degenerate, but the second plate is treated to provide a single direction of orientation. And finally, the last part of the talk will be about a uniformly aligned ferroelectric nematic and the electric field that is applied perpendicularly to the slab. So the first part, again, is very simple. You have a Petri dish, or you might have two glass plates. The important thing is that these settings do not impose any in-plane orientation of the polarization. And then you deposit a drop of ferroelectric nematic. It spreads and forms a uniform film. And you look at it under the microscope, and you see beautiful geometrical figures that resemble parabolas, maybe hyperbolas. This is the mode of polarizing microscopy, which allows you directly, instantaneously see the distribution of polarization field. It's a so-called pulscope. It's not the simulation, it's just the real-life texture of the ferroelectric nematic liquid crystal. So what you might see is that these conic sections are associated with circular geometry of polarization field, and they separate this circular domain from a nearly uniform domain in the far field. So the question is, are these really parabolas or not? And we just took the textbook definition of the parabolas and tried to fit the shapes with the equation of parabola, hyperbola, and we found that indeed many of those structures do resemble parabolas. Here you see that eccentricity is close to 1. But then we also might see multiple circular domains, and then the domain walls between them are close to hyperbolas. Here you see the eccentricity 2, eccentricity more than 1. And so the underlying physics is rather simple. Why do we see circular domains? Because in circular domains, the polarization catches its tail, and there is no deposited free charges. And it's also clear that unlike the sister deformation type splay, in ferroelectric nematics, the textures try to avoid splay. Why? Because divergence of P, which is the splay deformation, would produce the charge in the bulk shown here for the case when the negative charge is of a higher density than the positive charge. As a result of those bound charges, you would have again the polarization field now in the bulk of the material, and it should be avoided. So why the domain walls acquire the shape of conic sections? It's a very simple thing. It's the property of conic sections to bisect the lines that can be considered as either emanating from the foci of the two neighboring domains or as the polarization lines. So if I have two polarization domains, and if they have a boundary domain wall between them, this domain wall will not be charged if the normal component is continuous, but the tangential component of polarization is antiparallel from the two sides. Then you would have no surface charges. And that explains why the boundary that separates one circular domain from another circular domain is of the shape of the hyperbolic wall. The angle between the polarization number 1 and polarization number 2 is the same, and shown here as the function of eccentricity and the coordinate along the domain wall. And in the simplest case of coexisting circular domain and uniform domain, you have the parabola with eccentricity 1. Of course, these properties of the conic sections were known to the inventor of conic sections many hundreds of years ago. So I would remind to those who was here in 2019 and before that conic sections are not the first time seen in the Lake crystals. The classic example are focal conic domains in smectics, but the underlying physics and math are slightly different. In the smectics, one would like to avoid the bending of the normal to the layers, and curl n should be 0. But in the case of the ferroelectric nematic, it's the divergence that should strive to be 0 to avoid space charge and thus form a solenoidal field. The model of the ferroelectric nematics should account for the fact that the splay deformations are difficult, and here is what Dmitry and Peter propose. They kind of introduce the Frank-Ozen type of free energy density. P is the two-dimensional polarization. P, which is capital P with subscript 3, superscript 3, is the normal component of polarization perpendicular to the film. And as you might see, the divergence of P is supplemented with an elastic constant that is high as compared to the elastic constant in front of the gradients of P. And as a result, the simulations that are taken with this free energy functional reproduce the shape of the domain walls, shown here for the case when the circular domain is introduced by a seed that imposes circular boundary conditions at itself. This is this white disk. And everything else is more or less the same as we see in the experiment. Even the often seen kind of ghost parabolas that emerge from the tips of the true parabolas. They are also reproduced in this mathematical modeling. So one interesting thing is that if you look at the distribution of the polarization field, or optic axis, which is the same thing in ferroelectric nematic, you would realize that you can assign the +1 topological charge to the circular domain, but then you should find the defect that compensates this topological charge -1. And it looks like the system introduces two disclinations of strengths -1/2. And we know from topology that isolated disclinations of half integer strengths are topologically prohibited. And indeed, these two disclinations are being connected by the domain wall at which the polarization is antiparallel. So again, the physics of the occurrence of those two disclinations is very simple. As I approach the tip of the domain wall, the angle by which the polarization realigns increases and approaches pi. And at some point, it becomes too energetically costly. And what the system does, it introduces the -1/2 defect. On the left side, the polarization realigns by a large angle. But on the right-hand side, we simply have the antiparallel arrangement of polarizations of no elastic energy, but of course there should be some wall that transforms this orientation into antiparallel orientation. So to conclude the first part, if there are no externally imposed limitations on the orientation of polarization, the ferroelectric nematic would try to avoid surface charges and charges in the bulk by producing a lot of circular domains and conic sections as the means to separate them. So the next experiment is a little bit more complicated because one of the plates imposes unidirectional alignment. And of course, this unidirectional alignment would not like the circular domains. The question is how the texture would look like. We can start with the material in which we have normal nematic, which is of quadrupolar symmetry, and polar nematic, which is the ferroelectric nematic at a lower temperature. So if we prepare the cell in the high temperature, which is a normal nematic phase, then we see that this direction, which is denoted as R, Rabin direction, because the orientation is being imposed by the polymer film that is rubbed in one direction, it translates into the entire bulk of the material. And you can verify that this is a perfectly aligned nematic by shining light, polarized light through the sample, and then measuring the transmitted intensity as the function between the polarizer direction and the analyzer direction. If the two are crossed, then there is no transmitted light. If the two are uncrossed, then you have the light coming through, and its intensity is proportional to the cosine square of the angle between the two directions. So this is in the nematic phase. Now, all you do is slightly lower the temperature of the material and continue to watch the texture through the polarizing microscope. And this is what you see. The material splits into the domains of different contrast. You can see that the contrast would be complementary if you uncross the polarizer and analyzer in a twist left-hand fashion and right-hand fashion. And then you do the same experiment. You measure how the intensity of light changes as the function of the angle between the polarizer and analyzer. And then you fit this dependency with the twist of the polarization between bottom and the top. And you see that the agreement is more or less good. So the polarization being along the Rabin direction at the bottom twists along the normal to the cell. And in one domain, it twists to the right. In the other domain, it twists to the left. And the total twist angle is close to 180 degrees or 2 pi. So then if you add a little bit of ionic fluid, which dissociates into positive and negative ions, you might find that the domain structure gradually disappears. You find huge areas in which the polarization doesn't twist in space, and if you measure the light transmittance through those regions, you would see that there is no twist, no optical activity. So Maxim Lavrentovich calculated the balance of the depolarization field energy and the twist elastic energy for the problem in which one has a square piece of the substrate, and in the cell of the thickness H, one might have two different situations. Either the material is not twisted, but then there is depolarization field and electrostatic energy calculated here, or you might have a twist, in which case the depolarization field energy decreases by a factor of 4 if the rotation angle is 180 degrees, but you have the elastic energy. And the balance of the two would produce the critical thickness of the film. If the film is lower than a few micrometers, then it will be uniform. But if the film is higher than these few micrometers, then you would observe optical activity. You would observe polarization-induced chirality in the system. And you can also calculate what would happen if the material is doped with a sufficient number of ions. In that case, the depolarization problem would be gone and above some critical thickness, which is well achievable in the experiments. You would see a uniform texture, which qualitatively agrees with the experiment. We recently verified it for the photo-aligned materials in which both top and bottom produce non-polar unidirectional anchoring. And we see that in very thin films, the domains split into untwisted left and right polarization. But if the film becomes thicker than a few micrometers, then we observe the twist along the normal to the film. So the second conclusion is simple, that polar ordering and the tendency to avoid the polarization field and associated electrostatic energy leads to the spontaneous chiral symmetry breaking. The material splits into left and right twisted domains. Of course, on average, the amount of left and right twist is the same. And the structure is controlled by the balance of electrostatics and elasticity. Elasticity wants the domains to be as wide as possible, and the electrostatics wants them to be as narrow as possible, and the balance yields some characteristic size of those domains. Now we are coming to the classic geometry in which most of the applications of Licht crystals are used in your smartphones, in laptops, in the displays. What you have plates that are uniformly twisted, uniformly treated, and the nematic Licht crystal is placed between them, and there is an electric field that is being applied perpendicularly to the film by transparent indium tin oxide electrodes. And if the electric field is applied, then in the normal nematic, in paraelectric or nematic with quadrupolar symmetry, the director realigns along the field, and you have the change in effective birefringence of the material, and that or similar geometry is being used in display applications. Now, if the material is a ferroelectric nematic, then there is a polar order. And if I would consider a similar situation in a ferroelectric nematic, then I would realize that near the top and bottom electrode, I would have a splay deformation, because the surface anchoring at the plates would keep the polarization horizontal, and the electric field would try to realign it along itself in the bulk. So I would have splay in those two regions. And of course, the splay would create the polarization field that would oppose the externally applied field and will try to realign the polarization back. And in fact, many groups explore this geometry and said that there is no effect. The material does not respond to the electric field simply because very small realignment of the polarization is canceling the externally applied field. So we decided to use not just a DC field, but alternating current field of a very, very high frequency. And the idea was that maybe at high frequencies, the polarization doesn't play that much of a role, but the dielectric anisotropy, which is still present in the material, would cause the material to realign, and it would be of interest to see what would happen. And so we did the experiment, and it turns out that there is a very peculiar behavior in the AC field. We use high frequency, about 200 kilohertz, and go all the way to 1 megahertz, which is extremely high frequency. So when you measure the optical response by measuring the so-called optical retardance, which is nothing else but the kind of field renormalized birefringence of the material multiplied by the thickness of the cell, you see a very peculiar thing, that no matter how small is the field, there is a decrease in optical retardance. It's not a threshold effect as in a normal nematic. In normal nematic, you apply the field like to 1 to 2 volts and nothing is happening. But then the director starts to realign. Here, the realignment occurs immediately. And it turns out that this realignment is caused by the oscillations of the polarization. The polarization goes up and down with this incredibly high frequency of 200 volts, of 200 kilohertz. The question is, how do we know? Very simple. We put the cell under some angle with respect to the propagating light, and then if the polarization goes up or goes down, we see different optical response, obviously, because the angle between the polarization and the probing light is different. And this is the voltage that we send to the cell. The period is 5 microseconds. And this is the response. As you might see, the frequency is the same. There is the shift in phase. So whenever the voltage is maximum, the polarization is 0. When the voltage goes through 0, the polarization goes to maximum. So there is a phase shift of 90 degrees. Then you increase the electric field a little bit more, and you suddenly see that this homogeneous over the surface response is being replaced with a periodic pattern. You see the domains in blue regions. There is a twist. We can verify it again by changing the angle between the polarizer and analyzer. But the domain walls are in the form of splay deformations. And you might see that this splay is in the shape of lambda or in the shape of V letter, and those geometries alternate. So we again do the experiments with the tilted cell, and we run the optical responses, which are probably not that simple to understand. But the bottom line of this exploration is that we established that there is a stationary tilt of polarization. It's stationary moving down in one domain wall and moving up in the next domain wall. And the in-plane texture with the shape of V and lambda deformations supplements the similar splay in the vertical plane. And then you start to think, why do we have these splay regions, and why do they, what's the purpose of those domain regions? And then you realize that the answer is in the tendency of the system to reduce the space charge. Remember, when we apply the electric field, we expect the two regions to be of splay nature, and that would create the space charge. The component of polarization along the vertical axis depends on Z, and that creates the space charge. How do we reduce the space charge? We simply recall the elementary math, the definition of divergence P. If you have non-zero part here, then you can reduce it by producing the non-zero variation in orthogonal direction, provided that the signs of those two derivatives are different. Then the electric field induced space charge would be reduced by additional deformation in the plane of the field. So it's a very nice, purely geometrical solution to the electrostatic problem. If you have to have the deformation of splay in one dimension, then you can reduce the electrostatic energy by introducing the splay in orthogonal direction, provided the sign of those splays is different. Here I show if you have, for example, lambda deformation of polarization, which produces an excess of the negative charge, then if the vertical axis you had the positive charge, these two charges will cancel each other, and this splay cancellation reduces the total space charge. So then you induce, you apply even higher electric field, and suddenly you see that the geometry changes completely. Instead of the stripes, you start to see a lattice, well-defined lattice of +1 and -1 defects. that form a square lattice. And again, you do the optical characterization of those things. Here you see +1, -1 defects in the plane of the film. And you realize that the underlying geometry is also implying some cancellation of the splay deformation along the red regions. But you cannot do it in the entire space. There are regions shown in gray, in green, and in yellow, where the splay cancellation doesn't work. In fact, splay reinforces the field-induced splay deformations. And in fact, if we measure the voltage at the electrodes of the cell, we see that there is a uniform bias. We apply the voltage that has 0 time average, but the cell considers it as being a constant negative value, about -5 volt, and oscillations around it. And those charges create electrostatic field that drives electrohydrodynamics in the system and makes this plus-minus square lattices. So the conclusion for this part is that there is a nice geometrical approach to solve the electrostatic problem associated with the space charge simply by introducing the secondary splay in the orthogonal plane. So the problem is reminiscent of the minimal surfaces problem, the plateau problem, but the underlying physics is not the minimal surface, two-dimensional surface tension, but rather three-dimensional electrostatics. But in other sense, the mathematics might be similar. Finally, about possible applications of this wonderful material. So as I told you, many display applications are based on the normal nematics and their response to the electric field. The problem is that this response is relatively slow. When you remove the field, the material relaxes because of the surface anchoring at the plates, and this relaxation is passive. It's driven by the surface anchoring and the elasticity of the film. And so it's resulting in rather slow response times, about milliseconds for the typical material like pentyl cyano-biphenyl. It can be acceptable for normal display applications, but if you want to develop something like a light shutter, then it's too slow. The approach that would produce a much faster response is based on the changes in the scalar order parameter, not in the director orientation, but in the degree of molecular alignment. And our group demonstrated that you can achieve times that are orders of magnitude shorter, about 10 to 100 nanoseconds. But the problem is that in normal material, in normal nematic, the change of the birefringence that is induced by the field is relatively weak. It's about 20 times lower than the natural birefringence of the material. And so another very closely related effect to the one that I describe here is the Kerr effect. You start with an isotropic fluid, you apply electric field, it transforms into the nematic, and that is also a possibility, but the numbers would be approximately the same. So the ferroelectric nematics, unfortunately, if they are in the ferroelectric nematic phase and you apply this electric field up and down, the change in optical retardance is not that high. We recalculated it in terms of the angle of oscillations. It's less than 1 degree. So it's a small quantity. You cannot develop a robust optical response on the basis of these oscillations. And so we decided to use a different approach, which is a kind of Kerr effect in the ferroelectric nematic. And our colleagues at the University of Warsaw demonstrated that you can indeed transform an isotropic fluid into the ferroelectric nematic by an electric field if your material shows the thermodynamically stable ferroelectric pneumatic. Our problem was that we didn't know how fast this response would be. And this is what we did. And it turned out that the response is extremely fast. This scale is in microseconds. What you see here, the red is the applied voltage pulse, and in black is the birefringence change. You see that it's more than 0.1. It's almost 80% of the natural birefringence of the material. By the way, we again use the tilted cells. So if you translate the tilted cells into normal cells, this field-induced birefringence would be on the order of 0.16 rather than 0.12. And the material shows the phase transition from the isotropic phase to the ferroelectric pneumatic phase, but in the intermediate range of voltages, it's in the kind of bistable, biphasic region, and the response time in this bistable, biphasic region is rather large. But if you are below or above this intermediate field, then the response time is extremely fast. It's less than 1 microsecond. So this is the table that shows the comparison between the normal Frederick's effect, again, that is used in the applications of pneumatic, ferroelectric pneumatic, normal pneumatic, standard pneumatic in display applications. This is the figure of merit, which calculates the ratio between the field-produced change in birefringence divided by the response time, how quickly this change occurs. And so you have the figure of merit in single digits in normal pneumatic, but if you do the ferroelectric material and transform it from the isotropic phase to ordered phase, then you see orders of magnitude improvement. So to conclude, we demonstrated that the polarity causes chirality in the system to reduce the depolarization field. Splay, if it's introduced by some external means, such as externally applied electric field, can be reduced by additional splay, which is called splay cancellation of the space charge. And electrically modified order parameter of those materials is a very fast and very robust effect that might be used in practical applications. Thank you very much for your attention.
Thank you for this wonderful talk. The talk is open now for questions. Do we have any? Please.
Does P have a constant magnitude, or P, the polarization, does it have a constant magnitude, or is it?
Yeah, it's so we, when we observe the textures, it's a constant magnitude about 6×10⁻² coulomb per meter squared. Let me.
So that's per molecule. Somehow you associate us.
No, it's a density.
Is it that?
Yeah. So it's how do I? Is there?
There is. Okay.
Thank you. So P is about. So it's a dipole moment divided by the volume, which would produce you coulomb over meter squared. And this is the number that is close to solid ferroelectrics. And in textures like this, the polarization keeps its value everywhere. And we don't know much about the inner structure of the domains. Maybe there, the system either escapes into the third dimension through twist, which we see experimentally, or maybe in some instances the polarization is reduced. This is what Noel Clarke thinks in some of his publications. So at the domain walls, And in the centers of the circular domains, there might be some reduction in P, although I'm not sure.
Yes, please.
It's very exciting. Do you have any significant issues with backflow?
No backflow, because in the, I mean, in the first two stages of this electrically induced realignment, when the system is homogeneously oscillating up and down, we don't see any hydrodynamics. We verified it with the tracers added to the material. And we also do not see any significant hydrodynamics in this regime because, again, we verified it. The reason for the absence of those hydrodynamic flows in these two regimes is that the oscillations are very weak. It's about half a degree, which is practically, nothing. But once we go into into the square lattice, then here we see a lot of hydrodynamics. It's we think just an analog of hydrodynamic instability.
What kind of flow? Do you identify some geometry like circular?
These defects are being reinforced and stabilized by the hydrodynamic flow. So the +1 defects serve as the centers around which the loops of flows develop.
Thank you.
More questions? Yes, please.
Could you go back to that parabolic?
Right.
So you mentioned the two minus halves, and then there's the domain wall. So yeah, let's see that. So the domain wall is
This. This is where we see relatively sharp realignment of polarization. It's not the mathematical cusp, but it's where the circular domain meets the more or less uniform domain. So you have the polarization that is realigning relatively quickly, shown here. But as you go to the tip, the angle between the two approaches pi. And that it's like a hairpin. It's too much of elastic energy. And the system just avoids it by introducing -1/2 disclination and leaves the anti-parallel arrangement of the two polarization fields. So it's, in fact, a hybrid defect. It's a domain wall which is limited by a pair of disclinations. This is the Kibble mechanism, very appropriate to speak of it here at the Isaac Newton Institute, because those defects are what Kibble considered in cosmology.
Yeah. Thank you for the excellent talk. So maybe just a small question here, right? You know very well that domain walls, people classify them in different terms. That there's a sharp transition, there's a twist, right? People talk about Ising block walls. Can you say something on it?
Yeah, so Ising is, in our opinion, not very plausible case for the ferroelectric nematics. It's much simpler to deform the orientation of P rather than to reduce P to 0. In solids, it might be possible because of the aligning action of the crystallographic axis. Here, we don't think it's the serious possibility. So the domain walls are either of the block or nail type or both. And we see the deformations of twist and deformation of splay and bend. So I think that block and nail models or combinations of those is the more appropriate way to describe domain walls. difference.
And if I can, another question on a different side. So there you show the AC modulation of the ferroelectric. So and you show that this flipping of the polarization up and down at very fast rates. And so,
Yes.
so how should I think so? Your discussion was mostly in the P language, right? In the polarization language. How should I think about the director in this relation?
The
Right?
director, at least in the materials that we are studying, is parallel to the polarization. So when I speak of P, it's my personal opinion, I also speak of the director N.
Okay.
So the director does the same.
So there's no lag in between, especially.
No, I don't think so.
Okay.
So I have a quick question in relation to the previous slide we were looking at minutes ago. So there seem to be like two half integer defects, and then they are connected by, in this case, singular wall, you think, not solid.
No, I cannot say what it is. It's a sub-micrometer, 1-2 micrometers. So we do the attempts through electron microscopy to cut it and to see what's going on. But we are not done yet. The only thing that I can tell you is that above this tip, the polarization is in one direction. Below this tip, the polarization is in opposite direction. That I know for sure. I also know for sure that there is some twist when the polarization goes along the normal to the film. But that's all I can say.
So in this case, just curious if it's a good idea to split that defect into two half integers, or perhaps one could think about, just -1 with distributed core.
Yeah, I agree, totally agree with you. You can think about it the same way. By the way, this +1, we often see that it splits into the, as you said, distributed core, because it can be stretched into the membrane, if you wish, with 2 + 1/2 defects at the ends. That would happen if you apply electric field. But yeah, that's correct.
And how do you define the core? So normally in conventional pneumatics, we would think about reduction of scale order parameter and things like that. And here, what's your basis of definition?
You see the same change in the optical appearance. Even here, you might see that the structure is 1 till this point, and something similar till this point. But then at the tip, there is something that is different. So I can try to show in. Yeah, for example, here you might see the same thing. The structure of the wall goes more or less in the same fashion till this point and after this point. But in between, you have a different configuration. So, and especially here, you might see that this configuration of the optic axis is precisely of the -1/2 type.
More questions? Oh, let's see. Well, if not, it's time for coffee break. So let's thank Oleg Lavrentovich.